I'm Pete.
I'm Stephanie, and this is the Cool Part Show, our show all about innovative 3D printed parts.
Viewer mental exercise. Imagine a gas turbine engine, a small one like this. Picture disassembling that, if you can. How many pieces are you imagining? Is it like hundreds of parts, thousands of parts?
How about just two?
Technion Institute is experimenting with how far they can go to simplify producing a turbojet engine using additive manufacturing.
Radical assembly consolidation on this episode of the Cool Part Show.
The Cool Parts Show is brought to you by Carpenter Additive. When it comes to managing metal powder, there is no one-size-fits-all approach. Stick around after the episode to learn more. Welcome to the Cool Parts Show.
If you like what you see, make sure to subscribe on YouTube. You can also sign up for our all-access newsletter for even earlier notification about our new episodes. We are back in the studio with another 2023 winner of the Cool Parts Showcase. This was our best proof of concept part. It is a pre-assembled turbojet engine printed in one build, made up of just two pieces.
Just two pieces, except in this version, one of the pieces has been divided in half. So you can see inside there's a lot of complexity here because a conventional engine this size has a lot of separate components that all had to be fused together into this design of a one build, one material, two-piece turbojet engine.
This engine was developed at Technion, Israel Institute of Technology, and it was sent to us by Benny Chukarol. Benny is the head of the Turbo Machinery and Heat Transfer Laboratory inside of the Aerospace Engineering Department.
A gas turbine engine, as we call it, in principle is a very simple machine. So you have a compressor that compresses the flow where the pressure rises, and then we add heat to the flow in the combustor, and then we have a turbine that expands the flow. And at different temperatures, the energy that's required in order to compress and expand varies, and therefore there's residual abundance of energy at the exhaust. And this residual energy gets converted into kinetic energy in the nozzle, which is what we call thrust.
So, gas turbine engines used in a lot of applications. Could be connected to a generator for power generation. Engines like this are used in aircraft. A small engine like this could be used in a small, remotely piloted aircraft.
And the reason this is so potentially powerful is, as we mentioned in the opening, turbo machinery tends to be complicated. It's made up of a lot of different components. Those components are different materials produced by different suppliers, and somebody has to manage that whole supply chain, the sourcing and the assembly and all of that. And so getting to a pre-assembled design that could be made mostly in one build has a lot of advantages, not just for reducing the part count, but also streamlining the workflow and the supply chain.
So this is where it gets really fascinating. So all those different components, they're not there for nothing. They're all separate pieces because each one of those pieces has been specified or refined or optimized to perform its role in the overall system as well as possible. And the result of that is an optimally performing engine. But there is cost to that. The accumulation of all of those different precisely, carefully chosen components is the expense of all those different suppliers for all those different components and all of the assembly that's involved. So what if you flip that around? What if you impose a lot of constraint? What if you say, this whole engine, it's going to be made out of just one material. And it's not going to be optimized for the ideal possible performance, but instead, what if we design with the aim of simplicity? How simple and how cheap is it possible for an engine like this to be?
So essentially, through these design iterations, we managed to fuse all of the rotating parts into one subassembly and all of the stationary parts into one subassembly. On the rotating side, the monolithic rotor consists of the turbine at the bottom And as you are going up, you see the bearing journal, and then there's a compressor. Whereas surrounding it, you have the stationary section that consists of the heat exchanger, the nozzle guide vanes, the combustor and the bearing housing, the diffuser, and the intake. The novelty in this whole approach was to be able to create self-supported two parts that coexist, literally one inside the other, while not interfering with the function of one another.
I want to reiterate that it was not an accident that they ended up with just two parts. This was the intention from the very beginning. It was not the case that they designed all these individual components and then figured out a way of mushing them all together. They really set out from the get-go to come up with a design that would be as few components as possible, ideally just two.
What we did is we did a system level support-free design perspective for additive manufacturing that inherently incorporates all the stationary and moving parts and how they can be created in a self-supported way. And this was actually one of the main challenges. It would be impossible or nearly impossible to be able to come from a complex engine design and reduce the part count by fusing different parts and end up with such an architecture.
Technion Israel Institute of Technology. So this institute gets referred to as Israel's MIT. A lot of math and science and engineering talent, a lot of access to and connection to that kind of talent, and the team developing this engine drew on those resources, drew on that network for help in consolidating all these different components into these solid forms.
We are, in essence, in the lab, turbomachinery people, so we actually started the approach from reduced order modeling of aerodynamics. So we created tools in MATLAB that define each one of the components and how to be able to actually create them in a self-supported way. In the following, we did some fluid simulations in ANSYS. And at that point, we actually started a partnership with von Karman Institute for Fluid Dynamics in Belgium and Izmir Katip Celebi University in Turkey in order to be able to put together an engine that actually took the form that you have all seen. So while this was taking place, this was mostly a challenge of turbomachinery. We started also starting to encounter issues with the CAD design as well. And as you can see, the architecture is quite complex. So this is when we partnered up with PTC and utilized the Creo tools in order to be able to define the topology. So once the topology was defined, we checked for printability in materialized magics by slicing the different components. We did some process simulation in Simufact additive of hexagon, and we started printing samples. Once we printed samples, we scanned them. We have a Zeiss scanner here in the lab, and we conducted in Simufact additive this pre-distortion calibration that's required in order to get the architecture that we desired. At last, the parts were printed in EOS M290 and M300 printers at multiple locations.
So printed in multiple locations because Technion was printing in Israel, EOS was also printing in North America. But in both cases, the turbojet engine was made entirely from Inconel 718 through laser powder bed fusion. There's some minimal post-processing that happens after printing, so depowdering and heat treat, but the 3D printing really is the bulk of the production process, right? And so it's really important in that process to achieve the complex interior of this outer shell, and also to ensure that this rotor is going to be able to turn, to rotate almost immediately out of the printer. It was really critical to maintain a gap between the two parts, because if somehow they got fused together during the printing process, again, this rotor is going to be enclosed inside of the shell. It would be difficult, if not completely impossible, to separate them after the fact.
To be able to create this gap between the rotor and the stationary housing is one of the most challenging parts of the process, because the moment that you actually let go of your bearings, now you need to rely on the fluidic pressure, in this case the fuel, in order to be able to stabilize the rotor inside the housing. There were multiple approaches in order to be able to facilitate this. One of them was the design itself. So we wanted to make sure that the design would be self-supported on the rotor and the stationary components around it, and that's essentially what creates the journal bearing. But beyond this, we had to incorporate a lot of process simulation in order to make sure that the two parts, they wouldn't bend towards one another, and we would be able to retain the small gaps that's required. At the end of the multiple processes, we ended up with a gap of around 200 microns, which I would consider success from the perspective of manufacturing technology, but from the perspective of fluidic bearing performance, this is a big challenge still. And this is still one of the things that we are working on actively in order to be able to improve the bearing performance.
The engine is printed in two different pieces, but another way to think about that is the engine is printed. All of the rotating components are printed into this spinning portion. All the stationary components are printed into this stationary portion. And yeah, between them, there's that gap. Benny described that. The gap is there because that is where that hydrostatic bearing has to operate. And maintaining just the right precision of that gap during 3D printing for the sake of that hydrostatic bearing, that was one of the challenges the team faced. The team succeeded at meeting that challenge. And one effect, one payoff, is that in producing that engine, the team revealed just how much of the cost of an engine like this is due to assembly.
So the cheapest engine of this thrust class basically is sold for somewhere around $50,000 to $75,000. So whereas this engine, the manufacturing cost comes down to depreciation of the printer as well as the powder. So we are now talking about a cost of anywhere between $10,000 to $15,000 in terms of manufacturing cost. There's an additional fringe benefit, which would, I think, fulfill my vision, is if instead of engine manufacturers creating engines, what if the platform manufacturers would be able to just license out the design and print their own engines on demand? So this would be actually a disruptive change in the way that the entire gas turbine market is operating today.
So this whole idea of 3D printing a pre-assembled engine, it's not just an interesting engineering exercise. There are some real potential cost savings, like Benny just outlined. There are also the benefits of maybe being able to move or distribute production, like Technion and EOS already kind of demonstrated. There are also opportunities to maybe reduce the workforce requirements. Instead of that full supply chain of all those different manufacturers, all those different people involved, if you have one engineer and one printer making this design, you're producing the bulk of the engine in just one operation. All right, let's recap.
3D printed turbojet engine, all of the rotating elements consolidated into one rotating piece, all of the stationary elements consolidated into one stationary piece, two-piece 3D printed engine.
This is very different from how turbo machinery is typically made, being assembled from lots of different components. By consolidating the assembly into just the rotating and stationary components, they're simplifying the supply chain, simplifying, streamlining the workflow, and also introducing the possibility of distributed manufacturing, maybe even licensing engines like this to manufacturers. So the version of this engine that won the Cool Part Showcase in the category in 2023 was all about just demonstrating that it's possible to produce a pre-assembled turbojet engine that will operate like an engine. They were successful in doing that, and this application has advanced since then. Now it's all about iterating and improving on what they've already demonstrated.
We talked about the hydrostatic bearings, the importance of this. Well, there is a lot more to say about that. There are other bearing options that the Technion team explored, is continuing to explore. Our All Access members got to hear Benny talk in much greater detail about that, about bearing considerations, how they thought about the bearing that makes this engine work. If you're interested in seeing that, it is super easy. All Access membership is free. It's quick to sign up. Go to thecoolpartsshow.com/allaccess.
And if you have a cool part that involves radical assembly consolidation or some other benefit you're only able to realize through additive manufacturing, we would love to hear about it. You can reach us by emailing coolparts@additivemanufacturing.media.
Thank you for watching. This episode's brought to you by Carpenter Additive. We're past the point of not knowing how to qualify metal 3D printed parts. We know, it's just that different end users of those parts have different qualification requirements. Additive manufacturing service providers have to navigate that, and Carpenter Additive has to think about that in tailoring powder management solutions.
Our customers typically will have, if they are a service provider, they will have a series of end user customers who may be, say, OEMs in the aerospace world. And each of them has a fairly large team of engineers who've been doing this for decades or more and have developed all these standards, regulations, paperwork. So it is certainly a challenge to thread the needle between all of these different requirements. We start really high level, we walk on the shop floor, we ask them about, okay, source to sink, how do you bring in the materials, goods in, send that material to each of the systems, and then what we're really interested in is how do they reuse that material. So what we do is called a value stream map. Pretty often that leads to a series of things that were either overlooked or hadn't really boiled up to the surface yet in terms of things that are potential risks or potential challenges or inefficiencies that exist. A lot of the customers we work with, especially in the more regulated industries such as space or medical or aerospace, have already been through those early learning stages. They've put 5+ years into this. They've done the product design and the design for additive manufacturing. And now they're starting to reach some of the more finicky problems that you get when you're at the scale of maybe 5-10 machines. You're running different materials simultaneously, you're doing different programs. Right, we get to take the best from the medical field and the aerospace field. We understand the specifications and the standards that exist in each of those fields, and we can sort of take the best elements of those and customize that to our customers.